Okay, good morning, all of you. Let's get started. I hope you are following whatever is being covered in the class. In yesterday's class, I was telling that whatever elements we have seen, quadratic element, 9-node element or 8-node element, we have one node in the middle of the element. In the middle, in the sense, it's between the two corner nodes, you have a node, and the location of that node has to satisfy this condition, that it should not be too close to the, if you take this as these three nodes as part of 8-node element or 9-node element, one of the edges, this node should not be too close to these extreme nodes. These two nodes can be the corner nodes. So this node should not be too close, and it has to maintain a distance of at least quarter of length of that particular side. It should be at least quarter distance, quarter of the length of that particular edge distance from each of these two nodes. Okay, so that is one important thing. The other thing is the angle made by two edges should not be less than 15 degrees and should not be greater than 165 degrees. Okay, so these are the two points that you need to keep in mind. So now let's look at this validity of this mapping. Validity in the sense when this mapping is going to be good. Here you have this Jacobian. Basically, what we are doing is we have this actual element. With the actual element, we are going to map it onto a parent element. For 4-node element, this is how it's going to be. For 8-node element, this is how it's going to be. Depending on the location of the node placement, this mapping sometimes you may not have proper mapping. When I say proper mapping, let me go back to one-dimensional case, then it will be clear to you. You see, this is a 3-node linear element. Not linear, sorry, a 3-node line element. Okay. So here, basically, at that point when we were looking at it, I was telling, if you have a 3-node element like this, a line element, 3-node quadratic one-dimensional element, having 3 nodes at x1, x2, x3, this element we are going to map onto this element, where the extreme nodes coincides with s is equal to -1 and s is equal to 1, and the interior node coincides with s is equal to 0. Okay, so basically when we say we are mapping this element to this actual element, we are mapping onto this parent element. What is the meaning of it? The meaning is every point on the actual element is going to have a mapped point, a point on the parent element. Every point on the actual element will have a corresponding point on the parent element. And also that correspondence is only 1-to-1. So every point in the actual element is going to have one point in the parent element which it corresponds to. No 2 points will have, no 2 points in the actual element will have the same point in the parent element, or no 2 points on the parent element is going to be represented by the same point in the parent element. Okay, so there should be 1-to-1 correspondence. there should be one-to-one correspondence. So why I am telling all this is this Jacobian, if you plot it, it gives you an idea about whether there is one-to-one correspondence or not. That is particularly is going to be clear for two-dimensional case. So same thing. So whatever I just now explained to you, that there should be there should be something like one-to-one correspondence between every point in the actual element to every point in the parent element. Similar correspondence should also what is this? You see this people are logging in from outside the email IDs. That is the problem. So there should be correspondence even for two-dimensional case or three-dimensional case. Every point in the actual element should have one point in the parent element, or only one point. One-to-one correspondence should be there. Okay, so that you should keep in mind. And whether there is one-to-one correspondence or not, that is going to be reflected. That's going to be reflected by this determinant of J. We are going to see in some examples in a while. Okay, and please note that here determinant of J is going to be a function of S and T. Okay, so when we plot this determinant of J, then that plot is going to give you an idea about whether there is one-to-one correspondence or not. Or if you plot this X as a function of S and T, Y as a function of S and T, that also gives you an idea about whether there is any issue with this one-to-one correspondence. Means any issue in the sense there should be only one-to-one correspondence. No 2 points should correspond to a single point on either the actual element or on the parent element. That you need to keep in mind. Okay, so that we will see. So let's take an element like this. This is a 4-node element, and the node numbering is done in counterclockwise direction, and all the node number, these nodal coordinates are given. Coordinates of node 1, 2, 3, 4 are given, so you can easily write the isoparametric mapping. X as a function of S and T, Y as a function of S and T. X is equal to N1 X1 plus N2 X2 plus N3 X3 plus N4 X4. Similarly, Y is equal to N1 Y1 plus N2 Y2 plus N3 Y3 plus N4 Y4. So please take a note of it quickly. So these are the shape functions in the for parent element. This, even though actual element is looking like this, we are going to map onto a regular parent element, where S goes from -1 to 1, T goes from -1 to 1. In that case, the shape function expressions are these, and these are the nodal coordinates. Please quickly take a note of it. Please take a note of this. So hoping that you have taken note of this. So write the isoparametric relations. X is equal to sigma ni xi. So X as a function of S and T, Y as a function of S and T. And once you have X as function of S and T, Y as function of S and T, you can easily find what is this Jacobian and determinant of Jacobian. And determinant of Jacobian happens to be linear in S, linear in T, and you can easily verify whether between S is equal to -1 to 1, whether determinant of J is greater than 0 or not. Okay, so that is what is mentioned. It can easily be verified. Okay, or you can plot it. It's going to be a two-dimensional plot. S goes from -1 to 1, T goes from -1 to 1. You plot a three-dimensional plot in MATLAB or Mathematica and see whether this this equation, this plane, this is not an equation of a line. This is equation of a plane. Whether this plane is above the zero line or not. It is obviously it's going to be above zero line, so mapping is fine. So this is one way of checking. Or if you don't like to plot this determinant of J, what you can do is you can plot X and Y. You can plot X and Y between S going from -1 to 1, T going from -1 to 1. You plot X and Y. How do you plot? How do you plot? This is like a parametric equation. This is you need to just go back to your Mathematica or MATLAB and see how to plot parametric equations. Okay, and if you do that, if you plot X and Y as a function of S and T, S going from -1 to 1, T going from -1 to 1, if you plot it, that plot is going to tell you whether there is any issue with this mapping or not, whether there is any problem with one-to-one correspondence or not. So that particular plot, if you plot it, X as a function of S and T, Y as a function of S and T, with S going from -1 to 1, T going from -1 to 1 for this particular element. Please note that this element is not violating any of the conditions that we just discussed in the beginning of the class. There is no mid-side node, so the first condition is not applicable here. Second condition is the angle between the edges should not be less than 15 degrees and should not be greater than 165 degrees. And you can check here, this angle is not the angle between the any two edges is not violating that condition. So here this element is okay, but still let's plot it and see whether that is reflecting that or not. Okay, so if you plot X as a function of S and T, Y as a function of S and T, with S going from -1 to 1, T going from -1 to 1, this is how that plot is going to be. How to plot this? How to plot this? You please do. You just go to Mathematica or MATLAB and see how to plot parametric equations. Okay, and you can see here, and when we see some other example, you will understand this. If there are any folds in this plot, okay, if there is anything like folded, then there is going to be an issue. Anyway, here this is how. This X as function of S and T, Y as function of S and T, if you plot it, this is how it looks like. And there is no kind of any unusual thing that is actually reflecting here. So the mapping is correct. Okay. So now let's take another example. Let's take another example. So let's take this element. Intentionally, this element is taken. You can see here it is violating. It is violating the condition that this angle between the two edges being greater than 15 degrees, less than 165 degrees. That condition is violated here. You can easily see angle between this edge, angle connecting the edge, or the edge which is connecting nodes 2 and 3, the angle between this 2 and 3 and 1 and 2, it's clearly greater than 165 degrees. It's clearly greater than 165 degrees. And also this angle between 2, 3 and 3, 4 is less than 15 degrees. Okay? You agree or not? So now let's see. And first thing is how the nodes are numbered. They are numbered in the counterclockwise direction, 1, 2, 3, 4. So you write the isoparametric equation X is equal to N1x1 plus N2x2 plus N3x3 plus N4x4. Similarly, write isoparametric equation for Y and plot X as a function of S and T, Y as a function of S and T, with S going from -1 to 1, T going from -1 to 1. You plot it. This is how this plot is going to look like. You can see here there is a folding. This entire surface is folding onto itself. This entire surface is folding onto itself. That means there is no one-to-one correspondence. There are 2 points for which there is only corresponding 1 point in the parent element. There are 2 points in the actual element for which the corresponding point in the parent element is a single point. That is violating the condition. So here there is this kind of folding onto itself. That shows that mapping is not good. Okay. Here, a part of the element is folded onto itself. Is this clear? So basically, how we obtained this plot? We plotted x as function of s and t, y as function of s and t, with s going from -1 to 1, t going from -1 to 1. Then you get this one. Or the other way of checking is you have this determinant of j, which is linear in s and t. You plot this determinant of j, the surface of this determinant of j, with s going from -1 to 1, t going from -1 to 1. Check whether the surface is crossing the 0 line or not, a surface which is passing through 0 line. Is this clear? So here basically what is wrong with this element? This element violated the condition that angle between two edges should not be less than 15 degrees and should not be greater than 165 degrees. That is the condition which this element violated. So this kind of element, even though this appears to be a cooked up element, just to show you the implication of it, sometimes you may end up in getting these kind of elements when you are discretizing a particular domain. And if you use commercial software like NCS, Abacus, or some other software, they are going to you will see some warning messages. You will see the software, commercial software itself will check whether the quality of the element is good or not. And if that check is basically, the software is going to check whether this kind of thing is happening or not. If this kind of thing is happening for few elements, software is going to give you a warning saying that some particular element is not actually good. Okay, it's not a valid element. So this is one particular element where it's going to you are going to have a problem with the mapping. So let's see another example. So let's take this element, 8-node element. The nodal coordinates are given here, and the nodes are numbered in counterclockwise direction. Nodes are numbered in counterclockwise direction. And what this element should satisfy? This middle node for each of the edges, that is 2, 4, 6, and 8. These middle nodes should be maintain at least some minimum distance from the edge, the nodes at the corners for that particular edge. What I mean to say is this node 2 has to maintain certain distance between node 1 and node 3. It should not be too close to node 1 or too close to node 3. Similarly, other nodes. And what distance it has to maintain? How much distance it has to maintain? It depends on the length of this edge. So node 2 should be at least a quarter of a distance of that particular edge from node 1 or node 3. Okay, let's see what if it is violated, what it's going to happen, and what if the element is satisfying that condition, how that mapping is going to look like. So these are the coordinates. You write the isoparametric relation. X is equal to sigma ni xi, y is equal to sigma ni yi. So that for that you require to know down all the shape functions of the parent element. N1 to N8, this is the 8-node quadrilateral element, 8-node quadrilateral element. So you write the expressions for N1 to N8 and write the isoparametric relation, and also you find determinant of J. And here please note that for 4-node element, determinant of J is going to be linear. For 8-node element or quadratic element, determinant of J is going to be, you can see here, it's going to be quadratic in S and quadratic in T. Okay, it's going to be quadratic in S, quadratic in T. What you can do is you can check the mapping by plotting either X as function of S and T, Y as function of S and T, or this determinant of J. Both the plots are shown here. Determinant of J is plotted with S going from -1 to 1, T going from -1 to 1, and checking whether that surface, this surface, is above the 0 line or not. Or you can plot X and Y with S going from -1 to 1, T going from -1 to 1. You can see here, this is how this plot looks like. And there are no folds. For this particular plot, you need to check whether there are any folds. This particular plot, you need a determinant of J. You need to check whether it is above the 0 plane or not. This is a 2-dimensional case, so it's going to be a plane. Okay, whether you are above the datum plane or not. And here, this particular plot of X and Y, you need to check whether there are any folds or not. And here, there is no issue. This placement of nodes, everything is fine. So this element is good. This quality of this element is good. So now let's do a small experiment. Let's intentionally move this middle node 2 location. Let's change it and make it closer to node 1. Okay, that is what is done here. If node 2 is moved to 70, making it a lot closer to node 3. Sorry, node 2 is moved closer to node 3. This node 2 is moved, instead of, I just mentioned, you moved close to node 1. Instead of that, whatever example that is illustrated, in that case, node 2 is moved closer to node 3. What is the coordinate of node 3? Coordinate of node 3 is 0, 8. This is X is equal to 0. This is Y is equal to 0 line. This is Y is equal to 0 line. The coordinate here is 0, 8. Sorry, 8, 0. And this is 2, 0. And this is 4, 0 for this element. So this node 2, I am moving closer to node 3. Such a way that condition is violated. So I am moving to 7, 0. Please note that this length of this edge is 2, here 2, and this is 8. So length of this edge is 6. Quarter of that length is 6 divided by 4, it is 1.5. So this node 2 should maintain at least a distance of 1.5 units away from node 3 or away from node 1. But now I am moving it closer than 1.5. I am moving it to a location 70, which makes this node 2 location 1 unit away from node 3, violating that 1.5 units requirement. So I am moving to this location intentionally and see what is going to happen. As usual, you write the isoparametric relation as well as the determinant of J relation. You plot the determinant of J, or you plot X and Y as function of S and T. You can see here this determinant of J, if you closely look at it, it's going to violate because this surface is going to cross the 0 plane. Or if you see XY plot, you can see here there is a fold. Element is folding onto itself. or mapping is such a way that it's going to fold onto itself. So this mapping is not good. So this element, by whatever modified element, by moving node 2 to the location 70, that's not going to be a correct element. Okay. So these are the implications of these placement of nodes and the angle between the edges. That is what is illustrated here. Any questions? And one more example is given. I told you, I am repeatedly emphasizing, either you number the nodes in clockwise direction or counterclockwise direction consistently. If you don't number it, what's going to happen? Here, a 4-node element is taken, but the node numbering, you see how it is made. 1, 2, this node should be 3 and this node should be 4, but it is numbered as 1, 2, 3, 4. This node is numbered as 3 and this node is numbered as 4. What is the implication of this kind of numbering? That is what is illustrated here. So what's going to, what this finite element is going to think is, that actually this element is like this. When you do the mapping, x as a function of s and t, y as a function of s and t, or determinant of j, plot the determinant of j with s going from -1 to 1, t going from -1 to 1, or x and y, you plot x and y. Here plot of x and y is shown, and here you can see here, there is the element is actually getting like, as though this is a twisted. This plot is showing as though that mapping is twisted. So here also there is a folding, it's folding onto itself, so the mapping is not good. Okay, so you should be very careful with the node numbering. Any questions here? And if there are no questions, and anyway, we already looked at this numerical integration. So numerical integration you can adopt to simplify the whatever integrals that you are going to get. Okay. So now let's look at this one. Let's look at the general two-dimensional boundary value problem, which we already looked at earlier. Okay. Let me show you that one. With 3 node elements. So this is a general two-dimensional boundary value problem. What we did is earlier we noted what is the equivalent functional for this if we adopt variational method or Rayleigh-Ridge method, and how the equations are going to be if you adopt Galerkin method. Okay, and here the weight function is same as shape function, and when you adopt 3 node element, 3 node triangular element, there are going to be 3 shape functions. So I takes values 1, 2, 3. So now let's say I'm solving this problem instead of 3 node triangular element, I'm solving this problem using 4 node quadrilateral element. So because we just noted all the shape function expressions for all kinds of elements from 4 node to 9 node element, we can pick any of these elements and then we can solve the same problem. So now the same equation is taken, except I takes values 1 to 4. Here I takes values 1 to 4. You please go through all this. Already explained to you. This is Galerkin criteria. You need to apply integration by parts and Green's theorem and apply the boundary conditions. What are the boundary conditions? The boundary conditions for this particular problem, they are given here in the problem statement. These are the natural boundary conditions. This is the essential boundary condition. Apply these boundary conditions. and divide the boundary into two regions where essential boundary conditions are specified, where natural boundary conditions are specified. I told you all that explanation, whatever I mentioned while explaining for three-node triangular element is applicable here, except that wherever you see I taking values 1, 2, 3, now I takes values 1, 2, 3, 4. So here you are going to get 4 equations instead of 3 equations. Rest of the procedure is same. All the explanation that I gave for 3-node triangular element is going to be valid for 4-node element. So 4-node element also you need to number the nodes either consistently in clockwise direction or anti-clockwise direction. And simplification of all this is going to remain in line with what is already explained. Finally, you are going to get equation system like this. In this equation system, here it's going to be different because B matrix or Bx, derivative with respect to shape function derivative with respect to x, shape function derivative with respect to y is going to be different because here for 4-node element is bilinear element. So it's going to be different, and if required, you need to adopt numerical integration. So that's what is explained here. 4-node quadrilateral element for 2-dimensional boundary value problem. So you go through all this. Now you need to substitute these shape functions. So that's why I told you, you need to put your effort, okay? You need to understand, first of all, when you, before you try to understand 2-dimensional problems, you should have complete idea about 1-dimensional problems, the higher order elements in 1-dimensional case. And then you start with 2-dimensional problems. And what is the new thing when you come to 2-dimensional problem is this Green's theorem. Integration by parts along with Green's theorem. After that, everything is going to be straightforward, and try to understand for 3-node triangular element. Once you understand 3-node triangular element, replace the element shape functions with higher order elements like 4-node, 8-node or 9-node element. Then it's going to be easy to understand. Okay, so here the same equation system, except 4 shape functions are substituted because we are adopting 4-node element. All the simplifications are given here. So there is not much to explain or to teach as we go further, except that you need to put your effort. All the nodal, this 4-node element, all the nodal coordinates or the x coordinates are stored in this vector xn, y coordinates are stored in this vector yn, and then x as a function of s and t, or instead of writing x is equal to sigma ni xi, this that can be written as n transpose xn, y is equal to n transpose yn. And even the derivatives can be written with respect to s and t can be written like this. And Jacobian, we already noted Jacobian, okay? And this is nothing but the relation between the shape function derivatives in xy coordinate system to s and t coordinate system. And how you define bx, by, and derive this one, t interpolation of the field variable. Okay, with all this 4-node, adopting 4-node element, same general 2-dimensional boundary value problem, the element equation for 4-node element looks like this. You can make use of this and solve a problem, then it will be clear to you. So that is the purpose of giving you assignment 6. Assignment 6, if you say assignment 6, Assignment 6, there is a small lag in the the covering the required things, whatever is required to solve for assignment 6. So even though assignment 6 due date I have given as April 26, you can take till next week, because all the required material is not covered. Okay. So if you see this one, if you see this problem, 8th problem, you should be able to solve by whatever is covered. And the 9th problem, just now whatever we covered, based on that you can easily solve. And 10th problem and subsequent problems you will be able to solve as we progress. Hopefully by the end of this today's class you should be able to solve all these problems in assignment 6. Let's see that. Okay. So these are the element equations. Sorry, this is for 3-node triangular element. These are the element equations adopting 4-node Lagrange element, 4-node bilinear Lagrange element. Okay, and you can see here the last sentence what it says. The integrals involved in the element equations are quite complicated and usually require numerical integration. So you need to evaluate this. You may adopt the Gaussian integration. Changing the limits of integration from -1 to 1. Okay, changing the limits of integration to -1 to 1. You can integrate. You can adopt Gaussian integration. So here, how to do that? How to do that? This dA is there. dA is differential area in xy domain. What is the equivalent thing in SNT domain? dA is nothing but dx times dy, and in SNT domain, what is the relationship between dx dy and ds dt? The relation is through determinant of j. Dx dy is equal to determinant of j times ds dt. So wherever dA is there, replace with determinant of j times ds dt, and then all these derivatives you need to express in terms of s and t, and then limits can be changed to -1 to 1. So that is what is written here. One of the matrix simplification is shown. Once you have limits from -1 to 1, -1 to 1, you can adopt Gaussian integration. You already know what is Gaussian integration and how to get the weight function in the s direction times weight function in the t direction. A weight function in the s direction times weight function along the t direction, and get the grid of the integration points. All that, whatever you studied, and evaluate all the this entire integrand, that is kx times bx transpose times determinant of j. All this is all integrand. You need to evaluate all this integrand at each of the integration points, multiplied by the weights at that point, at those points. That gives you the total value of this. So this, how to evaluate this kind of thing for a particular problem, that is what is illustrated here. Here a 4-node element is taken, and the node numbering is in the counterclockwise direction, 1, 2, 3, 4, and kx is given as 1. And how to evaluate that particular kind of integral. This is a 4-node element, so you are going to map onto a parent element which is 4-node. S going from -1 to 1, T going from -1 to 1. So what are the shape functions of this 4-node element in the parent element coordinate system? That you need to make a note and do all the manipulation. And you can adopt 2x2 integration. It's mentioned here. Use 2x2 integration. 2 points in S direction, 2 points in T direction. So total 4 integration points are going to be there. So you need to evaluate at each of the integration point the value of the integral, this one, and then sum it up, all the 4 points. So here all that is illustrated very clearly. Point 1, integration point 1, what are the coordinates, and evaluate all the quantities. You see, so much calculation is required at one point. But if you do coding, then it's going to be, this all can be done in a split of a second. Okay? In few microseconds or nanoseconds, all this computation is going to be carried out if you do proper coding. So this is at integration point 1, integration point 2, 3, and 4, and sum it up. You get the total value of that integral. Okay? And if you see this one, if you see assignment 6, this problem, where is that? Here. Here, evaluate this matrix. Evaluate this matrix in problem. Sorry. In you please make an please make a correction. Please make a correction in your assignment 6. This is not problem 7. This is problem 9. This one you make a correction in your assignment. Okay. Assignment 6, 10th question. It's mentioned problem 7. It is problem 9. This figure. So please make a correction on that here. Okay. So for this problem, you evaluate this integral. How do you evaluate this integral? You need to find, first of all, get what is n transpose. And whatever I just showed you for four node element, dA is determinant of j times ds dt. And then limits goes from -1 to 1, -1 to 1. P is 2 here. P is given as 2 and use 3/3 integration. So here n transpose, and the dimension of n is going to be depending on, it's going to be a vector having 8 elements, column vector or a row vector having 8 elements. N is going to be 8/1 and n transpose is going to be 1/8. So total you are going to get 8/8 matrix. This Kp is going to be 8/8 matrix. Keep that in mind, okay? And that you need to evaluate using 3/3 integration. How to get the integration points, how to get the weights, all that you have done as a part of your earlier, this one, numerical integration. So adopt it and then evaluate this integral. So please make this correction. 10th question in assignment 6, this is problem 9. So that gives you an idea how to evaluate this area integrals. Even though here the assignment problem is insisting that you do on 8 node element, same thing you can already in here it is already illustrated for 4 node element. So you can easily do that. Okay? Any questions here? I'm not seeing any questions or comments from your side. I don't know whether really you are paying attention or not. Okay. So now, if you go back and see for triangular elements, how to evaluate the line integrals? How to evaluate these line integrals, that also I explained to you. Here, you are going to get these as line integrals. This one, K alpha R beta, you are going to have line integrals. How to evaluate line integrals? And those line integrals have to be evaluated along the element boundaries. And at that point, I was telling you or explain, this gives you an explanation for how to evaluate these integrals along each of the element edges. And please note that for 3 node triangular element, you have 2 nodes along each of the edge. Whereas here for 8 node element, you have For 8 node element, you have 3 nodes along each of the edge. Here, for 8 node element, you have 3 nodes along each of the edge. It doesn't matter. It doesn't matter whether you have 2 nodes or 3 nodes. You can follow the similar procedure, and here that evaluation of boundary integrals for 4 node element is explained. If you understand how you evaluate the line integral for 3 node element, you can easily extend the same thing for 4 node element. Because for 4 node element also along each of the edges, only 2 nodes are there. And when you are evaluating line integral along edge 1, 2, along the edge connecting nodes 1, 2, the shape functions of other 2 nodes 3 and 4 are going to be 0 along 1, 2. So if you write the shape function vector, for all the nodes alongside 1, 2, you have n3, n4 is going to be 0, and n2, n1, n2 are going to be similar to a one-dimensional shape function. So that is what is written here. For side 1, 2, the shape functions are going to look like this, because the shape function expressions are written for the parent element. So along this side 1, 2, these 2 node the values of these 2 shape functions, 2 and 3 and 4. 3 and 4 shape functions alongside 1, 2 are going to be 0, and also shape function expressions of node 1 and node 2, and we are evaluating along a side where t is equal to -1. So the shape function expressions are going to reduce to like this. It's going to be a one-dimensional case. So for alongside 1, 2, this is how the shape function vector is going to be. Similarly, alongside 2, 3, side 3, 4, side 4, 1. And the terms k alpha orbiter require integration over the boundary of element. Since the boundary consists of 4 line segments, 4 separate cases must be considered depending on the side along which natural boundary condition is specified, similar to what you did for triangular element. For each side, the coordinates S for actual element and corresponding S for parent element are shown. So capital S is denoted here, small s is denoted, and you see how this this arrow at this point, in which direction the arrow at this point. We are pointing, or this arrow depends on whether you are adopting counterclockwise direction or clockwise direction, consistent. And rest of the thing you can read it, and it's self-explanatory. Once you have this shape function vector, you can easily evaluate these integrals, k alpha and r beta along each of the edges. You need to spend some time, okay? You need to spend some time and understand this. You need to write isoparametric mapping along each of the edges. Side 1, 2. Side 1, 2 isoparametric mapping is going to be x is equal to n1 x1 plus n2 x2. n3 and n4 are 0, so those 2 terms are going to miss. What is n1, n2 along side 1, 2? That is what is substituted. Okay? And once you have this isoparametric mapping, derivative of x with respect to s, derivative of y with respect to s, that is what is plotted. That is what is given here. And Jacobian here for this line segment. What is Jacobian here? Jacobian always gives you a relation between differential element on the parent element, how it is related to differential element on the actual element. Here, what we are doing is integration along this edge. So differential element, when I say differential element, a differential line segment, a small line segment. S is the capital S is the coordinate or the notation that we are using here. Small s is the notation we are using. If I have a small element capital or D capital S, D capital S is a small element along this side, and what it corresponds to here, which is D small s. So D capital S, how it is related to D small s? It is related through Jacobian. Jacobian along side 1, 2. How do we get Jacobian along side 1, 2? That is all explained here. And D capital S can be written as square root of dx square plus dy square, and throughout the thing divide with the ds, and you are going to get this relation. So Jacobian along side 1, 2 is going to be length of side 1, 2 divided by 2. So the relation is capital D capital S over D small s is going to be L1, 2 divided by 2. And from there you can write what is D capital S in terms of D small s. And then you can evaluate each of these integrals. And this evaluation of each of these integrals, finally, you need to adopt Gaussian integration. So how to evaluate each of these integrals? Because as the integrand becomes complicated, you need to adopt Gaussian integration. And how to evaluate these two types of integrals, R beta and K alpha, that is shown for 4-node element. And example is also illustrated here. So you go through this example, okay? And once you have that, you can extend for 8-node element. Straightforward extension of that to the 8-node element. Only thing is dimension is going to increase. For 4-node element, shape function vector is going to be a vector having dimension 4 by 1, n is going to be 4 by 1, n transpose is going to be 1 by 4. And here, whereas for 8-node element, it's going to be 8 by 1 for n, n transpose is going to be 1 by 8. Okay, all this, you can go through all this. And similar to what is asked in assignment 6, for 8-node element, how to evaluate one of the matrix that is illustrated here. But here only one integration point is shown, whereas you are asked to show for all the 3 by 3 integration means 9 integration points. You need to show for all the 9 things, 9 integration points, sum it up. And also evaluation of boundary integral along the edges of a 8-node element. So along each of the edge, you are going to have 3 nodes. So those 3, the corresponding shape functions are going to be non-zero. Other things are going to be 0. There are 4 edges. Edge connecting 1, 2, 3, 3, 4, 5, 5, 6, 7, 7, 8, 1. How to evaluate these line integrals along each of the direction, and how to get the Jacobian along each of the edges. Everything is explained here. You go through it. For 8-node element, how to evaluate the line integral, that is also explained. So adopt similar kind of procedure. To complete this assignment 6, 10th problem. So here, to evaluate Kp, you need to adopt 3 by 3 integration. So total 9 integration points. Whereas when you are evaluating line integral, this integral, here it's mentioned 3 by 3, means 3 points along that edge, that particular edge. It's a line integral, so there is nothing like 3 by 3 for this line integral. 3 integration points you need to adopt to evaluate this line integral. So an example is given here. You follow that example. Sorry. You follow this example. And use 3 points. Here it is illustrated along side 1, 2, 3 using 3-point Gaussian integration, how to evaluate this K alpha. Whereas in the assignment you are asked to evaluate an integral which is named as R beta. What is that integral? Everything is given there. You follow this and complete assignment 6. Okay. So this completes all the Lagrange elements and as well as serendipity elements. Please note that here what is explained is how to evaluate this area integrals and boundary integrals, and a general two-dimensional boundary value problem, how to get element equations. That is what is explained, how to get the element equations as a part of this course. Given any boundary value, two-dimensional boundary value problem, you should be able to follow similar procedure, get the element equations, and then evaluate each of the area integrals and line integrals properly, and then solve the equation system. Okay, so go through it, and if you have any questions, please let me know. And so if you have any questions, you need to put effort, and then you need to ask. Otherwise, I'm assuming everything is clear. So in the next class, we are going to go to another topic. Here you can see here, I have only 4 topics left. I have only 4 topics left, and then the last date for instruction, I propose last date for instruction as May 7th or May 6th. But if it is not possible, we may have one or 2 classes on May 10th and 11th. And final exam is going to be on May 15th. So the next topic is going to be, please note that we have not looked at the triangular elements. We looked only 3-node triangular element. So how to derive the shape function for higher order triangular element, that is what is next topic. And afterwards, plane stress, plane strain cases, plane stress, plane strain problems, how to solve, axisymmetric problems, and then last one is 3-dimensional problems. Okay, so please put the effort and then try to solve the assignment problem, assignment 6, and if you have any questions, let me know.
Sir, hello.
Tell me.
Sir, one question from quiz 2.
Huh?
Sir, I have one question from quiz 2. Sir, in quiz 2, question number 3, can we solve that question using Rayleigh's method? Because the matrix we are getting is not symmetric.
Which one?
Question 3.
What is that you are saying?
Sir, I am able to solve it using modified Galerkian method, but not able to solve using Rayleigh's method.
That's what I told you from the beginning. Not all problems you will be able to put into the not all problems you will be able to use variational concepts and bring it into get the equivalent function. That's what I told you from the beginning. That's the limitation of variational method. So anyway, it's good observation. So I don't know whether other students have experienced or tried doing it. So that is the versatility of Galerkin method. Okay.
So sir, by looking at the question, can we identify without proceeding for solution? Can we identify that whether we can solve it using Rayleigh's or not?
Yeah, I told no. You should have second order derivative and fourth order derivative, even order derivatives. If you have, you should be able to solve using variational method.
Okay, sir.
Anyway, I think that's a good observation. That is a kind of thing. Please note that as a part of the course. Okay, unless you put effort and you ask questions. I don't know what is going on in your mind, okay, or I don't know what is your the working style or your thinking style. So it's not possible to cover various aspects. So this kind of observation is what is expected, and you can pose these kind of questions. Anyway, that's a good observation, and I think that gives you an experience that not all problems can be solved using variational method. But the versatility of variational method is all the structural mechanics problems or which we encounter in civil, mechanical, aerospace engineering. All these problems you should be able to solve most of the problems using variational method. Okay?
Okay, sir.
Okay, thank you. We'll meet in tomorrow's class.